Much like question 10, if you just watched that video, question 11 again asks us to determine some Laplace transforms. The difference being that this time we want to do it without directly using the definition of the Laplace transform. So in other words, we are relying here on some of the results we've obtained using the definition, but we're now going to apply those results directly. In 11a, we're looking for the transform of the function e to the 2t times t minus 2. And so multiplying a function by an exponential function, that's one of the cases in which we were actually able to establish a product rule for the Laplace transform, specifically the shift theorem. So again, just to make sure everybody's on the same page, the shift theorem states that if I've got the transform of a function that's of the form e to the power of some constant alpha times t times a function f of t, then the result I get is a function capital F of s minus alpha, where capital F of s is the transform of little f of t on its own. So in this case, then, the first thing I should do is I should figure out, well, what is the transform of t minus 2 on its own? Here I can rely on the linearity of the Laplace transform. So that's going to be the transform of t minus 2 times the transform of 1. The transform of t, and again, you can get this off the table of Laplace transforms if you don't remember it, is 1 over s squared minus 2 times the transform of 1 is 1 over s. So that's 1 over s squared minus 2 over s. So by the shift theorem, then, in order to get the Laplace transform I'm actually after, the Laplace transform of e to the 2t times t minus 2, I'm going to get the exact same result, but every instance of s is going to be shifted by alpha, which in this case is 2. So that's going to be 1 over s minus 2 all squared minus 2 over s minus 2, and that's all there is to it. There's no need to find a common denominator or anything like that. This is a perfectly reasonable answer to this question. Let's move on to part B. Kind of similar. Again, it's the Laplace transform of a product. Again, the transform of a product involving t minus 2, in fact. But this time it's the product of the step function, u sub 2 times t minus 2. And so, although I don't think we really give this a name, I guess I could call it the step function theorem for Laplace transforms. It states that the Laplace transform of any step function u sub c of t times a function of t minus c is equal to e to the negative c times s times capital F of s, where again, capital F of s is the Laplace transform of little f of t on its own. So in this case, happily, this is already in the right form for this particular result. I've already got my step function u sub 2, so c is 2 in this case, times a function of t minus c, t minus 2. In fact, it is t minus 2. So what that tells me then is that applying this result, the Laplace transform of u sub 2 times t minus 2, that's going to be equal to e to the power of negative 2 times s times the Laplace transform of t, because this result strips away the translation, the minus c part, and just leaves me with whatever function would be left without it. So in this case, I've got it written as t minus 2. but I lose the minus 2 part, leaves me with t. Well, fortunately, we've already identified in part A that the transform of t is 1 over s squared. So I simply get e to the negative 2s times 1 over s squared. And that's all I need to do. Moving on to question 12.